Good morning, class, and welcome to this lesson on momentum in two dimensions. We will be able to solve a problem involving a 2D collision between two objects. So just to let you know, there's nothing new in this video. There is nothing new in this video. But so far, we have dealt with one-dimensional collisions. So far, we have dealt with one dimension, okay? And one dimension means if this object hits this object, this is all in a straight line. But as you can probably imagine, this object could hit this object and they can go off at different directions. And so like I said before, there is nothing new here. We just have to make sure that we can break our momentum into its x and y components. And so basically, momentum in the x direction initially is going to equal momentum in the x direction finally, and momentum in the y direction initially is going to equal momentum in the y direction finally. These same equations apply. We just have to separate it into x and y. And what I can say about this is the only tip you need, the only chance of success you have is to have good bookkeeping. When I mean good bookkeeping, I mean labeling all of your variables, labeling all of your variables, making sure you have units and not confusing those items, okay? Because you're going to have a lot of variables because you're separating them into x and y now. You have to make sure that you have the correct numbers because it's very, very easy to get confused. Don't just plug numbers in because you will probably put the wrong number in the wrong spot. So let's take a look at a scenario here. We have two hockey pucks. Puck A, puck B. Okay? Puck A is approaching puck B is at rest. So the initial velocity of B is 0, and the initial velocity of A is 5.5 meters per second. Puck A weighs 0.025 kilograms. Puck B weighs 0.050 kilograms. After the collision, puck A heads this direction at an angle of 65 degrees, and puck B heads this direction with an angle of 37 degrees. Okay, so we have puck A and puck B. They're going in two different directions at these degrees. So let's separate this into its x and y components. Okay, the momentum in the x direction is going to equal the momentum in the x direction afterward, before and after the collision. So in the x direction, this A was moving completely in the x. So in the x direction, we have m, the mass of A, times the velocity of A initially in the x direction equals the mass of A times the velocity of A in the x direction finally, and this is going to be multiplied by the cosine of 65. Why the cosine of 65? Because this object is moving in this direction, in the x direction. This line right here is the adjacent side to 65, adjacent over hypotenuse, is going to be, and this is going to be the velocity of A finally, okay? And so that's that. And then this is going to be added to the mass of B times the velocity of B finally. And this is going to be multiplied by the cosine of 37, because this is a separate triangle here. This side is the cosine of 37. So that is going to be our first equation. Notice from this equation we know m, we know this, we know this, we know this, we know this, we know cosine 65 and cosine 37. We don't know these velocities. We don't know the velocity A final or the velocity B final, and so we have to figure those out. That means we need a second equation. Well, our second equation is going to be in the y direction. The momentum in the y direction initially equals the momentum in the y direction finally. So initially in the y direction, neither of these pucks are moving in the y direction. So initially it's 0. And that means that in the y direction afterwards, that means we have the mass of A times the velocity A final, okay, times the sine of, 65, because we are looking at this part now, and that is going to be, subtracting the velocity, the mass of B times the velocity of B final times the sine of 37. Okay, why is it subtracted? Because this one's facing up, this one's facing down. Opposite directions mean opposite signs. And so we can manipulate this equation, bring this over here, the mass of A times the velocity of A finally times the sine of 65 equals the mass of B times the velocity B final times the sine of 37. Now we have two equations, two unknowns. So we can manipulate this one and plug it into that one. So let's look at this on the next page. So here are my two equations rewritten. I want to solve for I'm going to figure out what velocity final B is. So I'm going to divide both sides by the mass of B times the sine of 37. Mass of B times the sine of 37. And what I'm going to get is V final B equals MA, V final A sine 65 over mass of B times the sine of 37. Now I just want to point out, we know MA, we know MB, we know sine 37, we know sine 65. We could plug all the numbers in here. We could plug all the numbers in here and just get a straight variable. And that variable is this. 0.752 times the velocity of final A equals velocity of final B. Okay, I plugged in 0.025 here, 0.050 here. I found these two numbers and I multiplied them all out. So all I'm left with is now this here. You can do this and that's fine. I'm going to keep sticking with the variables because I want to do it the more complicated way, just in case you have a question with variables like this, so that way you know how to do that. But you can always, if you have the numbers there, you can always do this as well. It's up to you. So I'm going to plug this into right there. Cosine 65 plus, I'm gonna write it down here, mass of B times mass of A, velocity final A, sine 65, mass of B, sine 37, times the cosine of 37. So this right here, I plugged in for that right there. So what do we need to do here? What we can do, first off, we notice that the mass of B cancels out. That's nice. We want to solve for velocity final of A. It is in both terms. So if we rewrite this again, mass of A, velocity initial of A equals velocity final of A. I'm factoring it out times mass of A cosine 37 plus this whole thing, mass of A sine 65 over sine 37 times cosine 37. Notice now in this equation here, we know all these. All I have to do is figure these numbers out, divide divide to find velocity final of A. And the final velocity of A is, 3.4 meters per second. And now that I have that, all I need to do is plug this in to right there. I put 3.4 in here. I work it all out. I get the final velocity of B. Final velocity of B equals 2.6 meters per second. Come on, pen. Okay, those are my two answers right there. So this was another example of two equations, two unknowns. Whenever you have something at an angle, a momentum at an angle, a glancing angle, let's go back to our first page, just like this right here, there's momentum in the x direction and there's momentum in the y direction. Momentum in the x and momentum in the y, and we treat those as separate entities. If we happen to know both of them, we would do the Pythagorean theorem to find out the actual momentum. So, like I said, there is nothing new in this video. We still have the same momentum equations. It's still all the same stuff. The issue is realizing that if something is at an angle, it has momentum in the x and momentum in the y.